Good morning, good afternoon, and good evening, everyone. Thanks for joining this session, Putting Resilience in Place. What we wanted to do today is talk to you about decision support tools, and particularly decision support tools that will get used by people more broadly. So why do I start with Google Earth and Google? Because actually one of the first things that people do is when they often address a lot of these sort of questions or geospatial questions, they will go to Google or those types of tools. So what we wanted to do in today's session is actually look at a number of decision-making problems which are more oriented at government and local governance, and sort of understand what would it take to have the types of tools that would echo the kind of go-to nature of some of the Google solutions that we're seeing, but actually link more directly to particular use cases and applications. And what we wanted to do today is, together with a series of collaborations and proof of concepts and actually applications that we've been doing with a number of the partners that I'll introduce in a moment, to take you through some examples of applying particularly geospatial and satellite imagery and AI to a number of very specific and concrete problems. So we'll call this where the digital rubber hits the road. And the applications that we'll be looking at today are around issues of local government and local government's decision-making, around service delivery points, in particular health applications, but ultimately also how this type of work comes together for decision support around planning, budgeting, financing, and executions. So I think one of the underlying questions around this work, and in terms of the applications of the different technology solutions, is more maps, more happiness. Do these technologies actually lead to better solutions and better development outcomes? So with that background, with each of the presentations, we've asked the speakers to talk a bit about sort of the why of particular emerging technology solutions. Is it because of the nature that they've been changing, or because they address a particular problem at the moment? What does the solution imply? How specifically has it been implemented, and how is it performing? And ultimately also, I think as a reference from today's presentation, is where can these resources be accessed by those of you in the audience or some of your colleagues? Now, we spend a lot of time, of course, on the platform side, the technology and the data and the digital workflows, but clearly one of the important parts of embedding these types of solutions are actually the people who are going to use them. And if you're working in, particularly in a government context, is the legal policy framework and the de facto practices. So in each of these practices, we'll actually look at how do the people that are supposed to apply or use these solutions also relate both to their formal and informal operating environment in terms of the decision-making that they do and the types of information that they can use. So to sort of put this in context before handing over, ultimately, of course, what we care about are the applications. Does a particular geospatial solution, decision support, whether it's in a disaster context or in a more regular planning, have an application, and is it being adopted on an annual basis? But I think what you'll see from today's presentation is that often the building blocks to that are access to the appropriate data, but then clearly the analytics that needs to take place in that. So is the data that is underlying the decision-making, and particularly if it's spatial, is it actually good enough for the application? And if not, what are the kinds of analytical or tools that can be applied to improve that data situation? So I'll end by saying that one of the sort of underlying frameworks for thinking about the data today, and some of the presenters that we've tried to structure this, is that bringing together different spatial data layers, particularly, for example, in the use cases that we'll present today around service delivery points, such as health facilities, the beneficiaries, the populations, and road networks, together with administrative boundaries, is clearly a very important lens of bringing that together. And the key to having tools that will actually get used is, of course, bringing these together in practice for the end user. So with that, let me briefly introduce the participants, the presenters today, and it's a pleasure to have Andrew Zolli from Planet, who will take us, the VP for Impact there, who will take us through photograph to film strip and give us a sense of what are we seeing in the satellite data revolution. We'll have Caleb from Microsoft AI, taking us through a tool that is actually using humans in the loop satellite classification imagery. Then we'll turn to myself and my colleague Anders Hofstedt from to talk about a use case example in East Timor that has actually brought together some of this type of information. And then we'll turn over to some colleagues from the Qatar Center for AI to show us how they've been using particularly innovative approaches to road detection to fill in some of the gaps in the use cases that we presented earlier, and then we'll bring it together. So without much further ado, let me, in that case, turn it over to Andrew, who's going to take us through the current state of satellite imagery.
Thank you so much, Kai, and thank you to everyone who's joining in wherever you are in the world today. I hope you're well. I'm going to share my screen, so give me just a moment. Let's see. I hope you can all see that. Can I just, Kai, ask you to validate that you can actually see what's on my screen?
Yes, we can.
That's great. That's great. Well, as Kai mentioned, I'm going to talk about a fundamental shift, a couple of fundamental shifts that are happening in the satellite ecosystem, and particularly the Earth observation ecosystem today, as they are germane and pertinent to the questions of how do we better monitor infrastructure, how do we better monitor development generally, and we'll use this. This is the sort of opening chapter, as Kai mentioned, on this longer journey from detecting change on the surface of the Earth from space to actually implementing policy change on the surface of the Earth using ever more finely refined information that comes from these sources. I thought I'm going to speak for about 7 minutes. I'll give you a very quick lightning tour of what's happening. And the first thing, for those of you who are not aerospace experts or satellite Earth observation experts, this is what a typical Earth observation satellite looks like. It's typically built by governments. They cost hundreds of millions to billions of dollars to create. They take decades of planning to produce, and they're quite large. They're beautiful, exquisite, rare, science-grade instruments, and we're all of us beneficiaries of these tools, but there aren't that many of them. And historically, they have been the provenance of very specialist actors. Organizations like Planet, and there both are and will be many more organizations like Planet, are leveraging the innovation of consumer electronics, and in particular, not so much the components, but the processes that shrink all those technologies down into very small packages like the ones you can hold in your hand, to reduce the size of satellites. This is the canonical Planet Labs Dove satellite. It's about the size of a loaf of bread, and we've put hundreds of them into orbit. When you make things small, you could make them less expensively. You can make them you can take different kinds of risks because you don't have to spend billions of dollars to take a risk to try something new. And you can fundamentally change the way in which you use these tools. So what we do at Planet is right now we have 150 or so of these satellites in an orbit around the Earth that orbits from the North Pole to the South Pole over the equator, between the sun and the Earth, and then up over the dark side of the Earth. And as the Earth turns sideways underneath, they collectively act as a line scanner to image every part of the planet every day at roughly 3 meters, a little more than 3 meters resolution per pixel. That's not enough to read your newspaper, but it's certainly enough to see many forms of infrastructure, every forest, every field, every city, everywhere, every day. And then we have a second constellation of very high resolution satellites that image at 50 centimeters per pixel. The distinction between these, which I'll describe in a moment in greater detail, is very relevant for monitoring infrastructure. The system on the left is very good for understanding gross level changes and understanding them everywhere. The system on the right is very good for studying fine level changes, but can't look everywhere. You have to know what you're looking for. This is how we put them into orbit. I'll actually skip this just in the interest of time. But just to say broadly, and this is beyond the scope of Planet satellites in particular, these instruments, broadly speaking, are following two curves of development. One is making them radically improving their quality in terms of spatial resolution and spectral resolution. the amount of the Earth that we're able to monitor in real time, and the frequency with which we revisit that place so that we're able to see changes happening on a daily basis. And the other curve that's happening is decreasing the cost per unit of that data. So the cost is plummeting, the quality is dramatically accelerating. And that allows us to do some things that are pretty remarkable. What you're looking here at on the left is actually the daily analysis of building out a new port off the coast of Kenya. This is a Chinese port that the Chinese are building, and you can literally watch the infrastructure grow in front of your eyes. On the right-hand side, what you're seeing here is the growth of roads infrastructure in the United Arab Emirates. Now, in both of these instances, these are not in the tropical forest areas. They're not in the they're in places where it's very easy to see the phenomenon. Let me show you a little bit about what it looks like, what these tools look like in detail when we're looking at regions of particular interest from a development perspective. And we've been working collectively in this group on areas of Timor-Leste and Vietnam. Here on the left, you see, this is the 3.7 meter imagery of one part of Ailu province, zoomed way out. But let's zoom into a little piece of it here. You can see in this red box, this is what the data actually looks like. And this gives you a sense of what 3 meter data looks like. You can see most of the roads. You can see some of the buildings. Obviously, some of the buildings are quite small. So details are a little bit difficult to get to. And this is unrefined imagery. This is the kind of raw imagery. This is the 50 centimeter imagery of a similar area in the same geographic region. If we zoom in there, we can actually see the quality of the roads. We can see their width. We can see much more detail about the buildings and what have you. And the reason this is important is because of what I'm going to show you right now, which is about clouds. So one of the things you may notice here on the left is there are no clouds in this imagery. And the reason there's no clouds in this imagery is this is a quite cloudy area, and it gets cloudy regularly. When we're able to monitor the same place continuously, we can then composite mosaics that strip all the clouds out. So over the course of a week, if you're able to visit over and over and over again, you can produce a perfect image of what happened in that space in that week. It isn't a picture of a single day or a single moment, but enough to give you a sense in that week, sort of what the current state of the art was. So for example, this is a picture of this very same place. This is a composite called a mosaic. And again, it's unreconstructed, but you'll see all the clouds disappear. This kind of data has enormous utility beyond the scope of the use case you're going to be hearing about today. We've done our own independent analysis and determined that it's relevant to 14 of the 17 SDGs, to specific targets and indicators, and you'll hear more about that today. But all of the promise of this, all of the work you're going to hear only can happen if we build the kind of industrial scale, scalable, reliable workflows, the kind of digital infrastructure to deliver this data on a continuous basis. So in addition to building the tools themselves, the data itself, we've also been building these platforms and infrastructures for delivering this data to people and systems on which it can, from which it can benefit on a regular basis. And with that, let me hand it over to Caleb to continue this story.
Awesome. Thank you so much. Let me just share my screen here. And you should be seeing the slides now.
Mm-hmm.
Give me one more second here. All right, great. So hey everyone, my name is Caleb Robinson. I'm a data scientist on Microsoft's AI for Good team. And I'm super excited to be here virtually with you all talking about this interactive land cover mapping tool that we're developing in collaboration with the World Bank and Ho Chi Minh City. So I'm actually going to skip around through my slides a little bit here because first I want to give you some context for this talk by showing you what land cover data actually looks like. So here we have satellite imagery, like Andrew just told us about, of the Nha Be district in Ho Chi Minh City. And on the right, you see the accompanying land cover classification of this imagery, which is a per pixel classification into classes like water, low vegetation, impervious surfaces, roads, and whatnot. So skipping back up, this lane cover data that I just showed is critical in a wide range of local governance and management challenges. So these are activities such as conservation planning, urban planning, etc. And it's not just lane cover data that's useful in these applications, it's up-to-date or timely lane cover data, because the decision makers actually need to have access to the current state of affairs, not just a snapshot of what the state of affairs looked like yesterday or last year or last decade. So now the problem is local governments face high barriers when it actually comes to getting this timely lane cover data. For instance, there's no sub 100 meter global lane cover data set that's constantly updated, and even accessing what is available is quite difficult. So at the same time, like Andrew just spoke about, there does exist these amazing high resolution satellite resources that we can take advantage of. And that's what this talk and really what the tool that I'm going to demo is all about. So we want to take the 3 ingredients that I'm showing in this slide, which are imagery, some ground truth data, and then AI algorithms or machine learning algorithms, and combine them in an easy to use workflow that lets local governments create lane cover data on demand. Again, we want to make local governments able to create their lane cover data on demand from satellite imagery. So without further ado, because time is limited here, I'm just going to jump somewhat dangerously directly into a live demo, which is always scary. So here we are. This is a web-based tool running on a virtual machine in Microsoft Azure. And I've preloaded the tool with a SkySat mosaic from August over Ho Chi Minh City. So I can just click here to start up the tool using that imagery. And this is the main interface of the tool. So we can see the SkySat imagery, we can zoom and pan around. And this is all kind of very basic stuff, but the main cool thing that this tool does is let you click to run a deep learning based lane cover model that will then paint colors on the screen based on what it's predicting the lane cover class for each pixel is. Now, because this is a unsupervised model that hasn't been trained on lane cover data, these predictions are total nonsense. But that leads to the second cool thing that this tool lets you do, which is interactively train these deep learning models. So what I can do is select the water class over here on the right, and then just click around on the screen to give this underlying model examples of what water looks like. I can do the same thing for built surface. So I'm going to say this is a building. I can do the same thing for tree canopy. We definitely have some trees over here. And again, the high resolution nature of the SkySat imagery makes these things really easy to tell. And the same thing for this low vegetation class. And now that I have all this done, I can simply press this retrain button, which will update the parameters of the model and show you the new predictions directly on the screen. So now any further time that I click will be with this new improved model here. And because you can see that it's still not making good predictions, it has some confusion here with the water, we can kind of continuously update it and go through the same process. So now this should be a better classification. Let's take a look at how it looks over here. And it seems to be doing pretty good. So you get the picture. You can kind of iteratively refine this model. And there are a couple other bells and whistles that we've been developing here, like the ability for local users to define polygons, maybe run the model over a larger area and get the output as either a PNG, a GeoTIFF to use in their downstream GIS workflows, or even do simple things like look at the class statistics over the area. So for example, this area is made up of around 44% impervious surface. So there are a lot of kind of other bells and whistles, like I said here, but this is a very short presentation, so I'm going to jump straight back to the slides. And we've been working on this workflow with a variety of imagery. So there's a lot of machine learning work that goes into this, but we've tested this out with Sentinel-2 imagery, which is a public data source at a lower resolution, and then a whole suite of commercial imagery that allows users of this tool to really make these classifications at different resolutions. And just to summarize, because I think I'm at time here, the key points that we want to have you take away is that land cover data is very important for supporting a variety of different planning applications. It's hard to get at, and classifying high resolution satellite imagery with machine learning pipelines is really a promising approach for creating such data and allowing, importantly, local governments to create such data. And we're trying to make this whole pipeline easy via creating interactive tools. So with that, I'll turn it over to the World Bank. Thanks everyone so much. So we can't hear anybody if you're trying to present.
Hi, can you hear me now?
Yes.
We can.
So let's actually sort of work to sort of how does this bring together in terms of better data. So this is going to be jointly with Anders Hofsteg from Catalpa, which is a tech for development firm out of East Timor. So what I'm going to present to you is actually a slightly different view of, you've seen a lot of mapping data now. And the question is, well, how does this actually matter for planning decisions? So what we're going to present to you very quickly is some work coming out of Timor-Leste, which actually started as a public expenditure review, which is a sort of traditional way in which the World Bank looks at expenditures of governments. In this case, the objective was to look at expenditures on the health facilities. I think quickly the government and the different agencies raised the concern of, well, how do we actually sort of review proposals of upgraded health facilities to achieve some minimum standards? And the question was the access rates to within certain distances of the population to these health facilities. And so the approach that was taken was to sort of begin to understand to what extent does the population actually meet objectives of accessing these health facilities, and particularly within 2 kilometers or 5 kilometers, which then of course required modeling the road network, because typically you would assume that the population would travel to those areas. And so when you then took a geospatial planning approach to this, you quickly needed to ask yourself the question, well, how would you optimize new facilities, or where would you place new facilities? So what was done was actually setting up an interactive tool that first of all tried to map all the information, and then similarly to what Caleb was showing, is begin to provide users with the opportunity to provide feedback on that data to say whether these data were correct. And if the key ingredients to Caleb's land use classification mapping were imagery, algorithms, and labeling and training here, the key ingredients here for this optimization tool, we're asking where were the health facilities, where was the population, and where were the roads. So we'll run you quickly through this tool, which is the Geospatial Planning and Budgeting tool. And what we quickly found actually was that if you did this modeling for the government, you could typically access what we often find in academic work or a lot of the NGO work, that publicly accessible data sets were being used. So these were OpenStreetMaps or health facilities that were in the public domain, for example, scraped from Google and other health facilities. But that the data that the government was using on the right, the road networks, were actually different data. And those data had gaps. And the question really was not just how do we improve this data, but what difference does it make? So with the geospatial planning and budgeting tool, what was actually done was an optimization that allowed the user to incorporate different types of data and not only generate the optimization, but also look at the sensitivity of different data on it. And then I think bringing the the class of uses together is say, if you actually use satellite technology or others to improve the data, what changes in the results does it make? So let me make this more explicit with a curve here. If you look on the left-hand side, just to quickly orient the viewers to this curve, this is the y-axis is the percent of coverage of households that are covered by health facilities. The blue line is the ones that are within 2 kilometers of a health facility, and the red line is those that are within 5 kilometers of a health facility. So the red line, of course, is a less stringent standard. East Timor has about 350 health facilities. And so what you see on the left is based on one set of data combinations about the road network that I previously showed you mapped, you were getting baseline statistics of what the performance was. What the optimization model also does, and I won't go into too much of the details of it, it then tells the user, where would you optimally place the next health facility to increase the access to the next higher level? So if you see the lines moving upwards, it basically shows that by adding another 100 or so health facilities, by moving from 350 or so to 480, you would actually get to 100% health facility coverage, primary health facility coverage in that. But the second graph showed that if you were using different data or different road data from the official data or versus the unmapped, the public data, you were getting different results. Now, I won't go into the details of this, but simply one issue was that the government was making decisions to the road data that was official, but the open data was a different data set. So what we tried to do is actually begin introducing both more systematic human-based approaches, but some of the machine-based approaches to try to determine how could you actually get to a more convergent view of those road facilities that were there. And here you see the picture of the result, which are, if you ask the platform, what would be the next 10 facilities that you would place ideally, then where would you place these? And this gives a very interactive sense where the user can then zoom into those types of facilities and understand where there might be underserved populations. This then gives the results in terms of the number of facilities, and adding budget numbers, you can then determine what would be the cost. So for example, with OpenStreetMaps, the model suggests that 80% of the population, there's no need to add additional facilities if you want to get to a threshold of 80%. If you'd like to get to a threshold of 95% at 5 kilometers under the OpenStreetMaps, you would need to add 1 health facilities. But if you were using the official data, you would need to add 34 health facilities. Now, the point of this is simply to say that not just the modeling or the budget modeling makes a difference here, but actually the investments that you've made in the quality of the data do make a tangible difference. You can get very different results based on what data set you're using. And so the key point takeaway is saying that investing in the data and actually making sure that you at least have a convergent view of what the data is, or at least have a convergent view of what is the data, the roads data that the officials are managing to, or the health facility data that the officials are managing to, and how is that being agreed to, is actually critical for some of the results. So with that, let me turn it to Anders to basically bring his perspective from East Timor of how we then took these findings, which in some senses are technical and while digital, perhaps may not immediately resonate with some of the key counterparts. So over to you, Anders.
Thank you. So at Catalpa, we like I was saying, we try to leverage all the promises and benefits of technology and actually make it contextualized so it's useful within developing contexts. So in the case of Timor, as you saw in the satellite imagery, it's an incredibly mountainous country. Yeah, and it is very difficult to conduct the simplest of tasks. So one of the things that I'll bring up later is how this information be actually useful on the ground and at each level of service delivery. So the key to that is actually understanding who's going to be using this information, because if we can't make it relevant for the people at the different levels, of service delivery, whether it be at the Ministry of Health, Ministry of Public Works, or the person on the ground at the clinic. If we can't make that case to them that using this technology and using this information is the pragmatic choice, then we're missing a great opportunity. And at the moment, there is one of the challenges is that there is a lot of fatigue on people making promises on technology and not delivering. So again, we have to ground these things in what are the basic needs of these individuals. And to do that, as may look familiar to some, we create user personas. And so for each level, from the ground level at the clinic to the national level, we have we form a persona, so we have a better understanding of the needs, the requirements, the responsibilities, the daily workflows of each person at this level. And then based on that, we can kind of formulate what is the benefit to these people. How do we kind of curate the information so that it is actionable at each of these different levels? And if Kai could go to the next slide. So this is a story of 4 Timors. Yeah. What you have here is 4 different maps of East Timor with OpenStreetMap roads data, and then data from the Ministry of Public Works, which is through the Estrada platform that we helped build with the Ministry of Public Works and ILO, so that the national government can actually monitor and manage their road network. Now, the red dots that you see, those are households that are out of reach of the road network. And using the different thresholds that Kai was making reference to before, 2 kilometers and 5 kilometers. And you don't have to look really closely, but you can see that based on the different types of data, you get a different picture. Straightforward. But what that means in a practical sense is it determines the decision that the national level will make for where to focus its limited resources in terms of like logistics, or in the case of vaccinations that will happen next year, you know, what is the investment that the government needs to make in order to maintain a supply chain, get partners mobilized to kind of deliver those services. And so it makes a difference where this information is coming from. And in the case of the Estrada system, what we see is that the road network is more fleshed out. And so the decision of where to go is more focused. We can have a more granular approach to where to decide to invest these resources. And if you could go to the next slide. But what this means in a practical sense is that there's a lot of legwork. And so what you're kind of seeing here is that we have a funnel from the satellites that Andrew showed and some of the machine learning techniques that Caleb showed and that we showed later. You know, how do we distill this information? This is the challenge. How do we distill this information to socialize it at the different levels? In this case, you'll see Elizabeth, which is using high technology in Timor, which is a printer and some mobile phones and such. And how do we get this information in a factor? So here we have a nice little map with the road network overlaid with the households and the health facilities, and getting this to the facilities so that we can actually build that feedback mechanism that Kai was talking about, and getting some ground truth and some what's the word I'm looking for? Reality checking, kind of our assumptions, so that we can ensure that these tools are pragmatic and they're actually serving each of these personas that we've created. Going back to that image of the 4 Timors, one of the challenges is how does the ministries and partners, how do we flesh out the data? How do we flesh out the road network information in a way that, again, is practical and pragmatic, so we can actually increase that resolution, increase that granularity, so that the limited resources of Timor can be more focused. And it is by that we can say, this is, again, pragmatic. This is practical. This isn't just a dream of people from Western countries. And And this is our challenge. And I think we actually have a really great opportunity here to make that case, and probably for the first time.
Great. Thanks, Anna. So I think with that sort of reality check of how this data is actually sort of moving from Andrew's sort of satellite vision and the intermediate in terms of some of these steps of processing it and being able to print it out, let me now turn over to Lokendra Chowdan and Sanjay Chalwa from the Qatar Center for AI. And we've been working together with Planet over the past months to actually try to see whether AI-based approaches can actually fill in some of those road gaps, and actually just demonstrate whether it is actually possible to bring AI approaches within a context of a workflow that actually gets satellite imagery to an actual sort of decision-making inside point of view, focused back on some of these local governments. So with that, Lokendra, do you want to just go ahead and share your screen and present your last section?
Okay, yeah, sure. I'll go ahead and do that. Thank you. Okay. Hi, everyone. And thank you, Kai, for handing it over to me. Now, I'm Lokendra Chauhan from Qatar Center for Artificial Intelligence, and I'll be sharing on behalf of my colleagues and others, like how we use AI to build better maps. Now, as Kai and others have already
begin full screen.
Yeah. As Kai and others before me have already outlined why accurate maps are critical and the importance of using AI and satellite imagery for other applications, I'll just move ahead and try to give you an overview of what we plan to do here. Now, we start with satellite imagery from the likes of the way the planet is provided. Now, and then overlay existing maps like OpenStreetMaps or government records on top of it. And then our AI-based system is used to infer maps and then on which reviewers can fix any errors the way Andres was talking about. Now, after that, we can take the whole stack and put it into any other use case layers, the kind of layers Kai was mentioning about, the GPDT tool, etc. Now, so this is an overview. Now, what happens is like going slightly deeper, when you get a satellite imagery, the way classical AI methods for map making work is somewhat different, and they don't work very efficiently on the map making problem specifically. First, they look at each pixel and determine the likelihood of it being a road or not. That's a raster output, which isn't usable if you want to determine the driving distance between 2 points on a map. Now, so they have to do a lot of rule-based post-processing to create usable vectorized road maps, which is what we use whenever we want to find directions for going from one point to another. Now, this is quite difficult to get right and requires a lot of manual effort too. So which is where we came and we started. We have built an AI-based system, which and these new algorithms, like as you can see in the image, they take satellite images directly, and then we directly provide a vector output, which is what is needed. And the way in this particular case, the way it does is we take GPS traces also to make the initial set of the map. It takes care of the main arterial roads, etc. And then we use another algorithm which then goes ahead and tries to create the interior roads, the road network. Now, often we use often we directly go ahead and use the second algorithm because that can take care of arterial roads too. Now, beyond the like of what you would notice is that due to many reasons, like computers can't always get the road networks right. So which is where we also build a map editing tool. Now, what it does, it gives the reviewers specific suggestions on, okay, these are the road segments, which is where computer system has a doubt, and the reviewer can review and decide whether that's indeed a road or not. And that's how the system works. So this comes on top of the algorithmic map inference system work we do. Now, here's a list of all the different projects tackling different aspects of improving roadmaps that we have been working on. Now, we started with road detection, then incorporating map editing and inferring road attributes. Now, our vision is to build an AI system that can automatically update maps using satellite images and by seeking feedback from human reviewers wherever needed, without any coordination from people in between, because right now there are a lot of manual steps which happen. Anyway, that's the ideal situation we want to be in. Now that I've shown you the promise of our work, we need to show why it is valuable. And coming back to what Anders was mentioning, like when you have, in fact, this was a specific question which Anders had asked once, like if I already have a map and I know which road segment is missing, why can't I just use the marker and put it on top of it? And which is where, so that's the approach I want to take you to explain this thing. Now, all of you must have played once in your life, definitely played this game of spot the differences between two images. Now imagine if you had hundreds or thousands of theirs. Would that be fun, or would that be tedious? And what if it goes to millions? Now that's where computers come in. Once they learn how to find an object, they can keep doing it forever without making the same mistake again. They will make different kind of mistakes, but then those could be corrected using human feedback. So that's where we're we're building a system that has human in the loop and is in charge of all the decisions. Now, people have a lot of tacit and contextual knowledge, as Anders was also talking about, that computers don't. So that knowledge needs to come in as human feedback, and which is why I think it's easier and better to let computers do the majority of grunt work and let people fix computers' mistakes and take call judgment calls, which in turn improves the performance of the overall system. Now, this is the high level. I hope I was able to make a case for why we should be using AI for making maps. Now, I'll bring in my colleague Sanjay to add some more stuff.
Yeah, just one point. What Lokendra mentioned right in the beginning about typically when you do this, when you infer the maps from satellite imagery, bypassing the step of pixelization, going directly to the vector maps. I think that's the key innovation that this project is bringing in. And there's always a duality in spatial analysis about the field view versus the raster view versus the vector view. And this project is trying to bridge that, and also, in a very tangible sort of way. And the slide that now he's showing, it's not just, sort of inferring the vector maps, but also then doing some meta level information about maps, like predicting the type of the roads, type is the parking lot or not, and also then making the maps more realistic. So in the middle, bottom in the middle, you have an output from the road map, then use another AI tool to actually make the lines more straighter. And of course, he mentioned about AI augmentation, sort of human in the loop, where we take feedback, like pretty much like what Kaleb showed, but applied for road networks. So yeah, I think so. It's a whole suite of AI tools that we are trying to build, and hopefully we can collaborate and add value to the end user. Thank you.
Great. Thanks very much. I think if people have questions, we still have about 10 minutes. I'll just wrap up very quickly. Lokendra, why don't you just bring me to the last slide, and then we'll begin taking some questions from the Senate. I mean, I just want to sort of echo one thing. I think what you've seen here today is a bringing together of a number of presentations and a set of collaborations that have occurred over the past year or so. Perhaps the main message is that, while the technology kind of is always promising and it gets to that stage, I would say about 80 or 90% of the work, at least from the perspective of us of bringing it to the final client, has been on simply getting the digital workflow and the logistics down. So the step of moving from sort of the lab or the sort of what is in theory on the cloud to the actual being able to print it out and get the feedback on the ground, or to simply add a tool like the tool that was being presented by both Microsoft and the Qatar Center for AI, and bringing that to bear on a local set of data is really the sort of the piece that'll get you to the end user. So these shouldn't be underestimated, but perhaps the promise of that is that you are able to then replicate those tools and more flexibly have them speak to different types of data. So getting back to the example of Timor-Leste, we are now able to sort of engage these tools, or in Vietnam, engage these tools with the data that's given by the local counterparts, whether it's their e-strata system or it is their own land use classifications and the typologies that are made, and flexibly adopted to that, rather than giving them a tool that is a cookie cutter that is simply set for global data. And I think that would be one of the main takeaways, hopefully, that you'll take from this presentation or any follow-up with the different teams. Just to conclude very quickly, and then we'll check the chat, is I think the key lessons that we've had on the so what, or the user value added, and this is, I think, something that has come out more and more clear for me over the course of this, is in terms of looking at the different AI tools that these teams have presented, is there simply an example of automation or augmentation benefits here? Is it simply that you are trying to get a fancy computer to do what you could do with a marker, or are you actually able to augment the process? And we would argue that from the findings, that you're actually able to extract more information more systematically, more consistently out of imagery where the human eye may not be able to tell so much. So I think one of the things that we have found, for example, that on the high resolution, the high frequency imagery, but lower resolution imagery that is coming in a daily cadence that Andrew was presenting, these tools actually become, after a while, quite necessary, because having humans go over daily imagery at medium resolution is simply not possible. So these machine-based tools are more about augmentation rather than simple automation. The second, I think, point of that we hope you take away is call it what we call the warning of, is this a UFO or a pragmatic solution? I think the UFO term, I think, thanks to Anders, are we flying in with technology that is really so removed from the day-to-day concerns of the counterparts, or are you actually increasingly able to bring these AI and satellite solutions to become the pragmatic solutions, even for somebody who is really just looking at a banner map, but who does see then the value of using these types of tools? And we would argue that, at least for the cases we try to work very hard to make it more towards the pragmatic solution rather the UFO landing. I think the final point, both of these products or processes that we presented today, in terms of the raster classification that Khaled has presented, and the more advanced, I think, vector-based classification that Lokendra and Sanjay have presented, is really ultimately what's the minimum viable product in terms of capability and complexity, but ultimately also cost. And it's not just the capability, but it's really the complexity that is the barrier to access. If it's simply too complex to relate this tool to a local road asset system, or too complex to get the data, then it doesn't matter. And ultimately, I think cost does matter. So let's end at that, and let me see if my colleagues have already taken a look at some of the chat comments, and we can begin responding, or if people would like to pull in some points. I see a comment from Chin Hui. I hope I'm pronouncing that right.
Yeah, so I can briefly mention about the topological changes. In fact, yes. So this project that that we worked on in Qatar was actually motivated by the constant changes in Doha because of the preparations for the World Cup, FIFA World Cup 2022, and the roads were constantly changing. And one of our objectives was actually to automatically infer what road network, what topological changes are occurring. So so partly it answers that question that Shihui has.
If I could pick up on Shihui's question, it's a great question, and I think it might be useful just to think about what the future state looks like. So as you might remember back when at the beginning of the presentation I was discussing, we have these two satellite systems, and putting aside the fact that they come from Planet or the fact that there's some proprietary technology, they represent, broadly speaking, the two techniques that I think we're going to see a lot of. One is continuous higher and higher resolution monitoring of the planet on a passive basis, so that we look at Bangladesh and Beverly Hills and Beijing with the same frequency, the same resolution, the same cadence. That continuous monitoring that is essential for understanding change and understanding the kinds of changes that happen, particularly when a natural disaster occurs. And particularly what's of relevance is understanding what the system looked like the day before the system was perturbed, the day before the landslide, the earthquake, the flood, and what have you. But those continuous monitoring systems, for all kinds of reasons, some of them economic, some of them technological, are likely to be lower resolution. So one of the things that we're seeing is that increasingly, as we automate the extraction of classification and feature detection in that lower resolution data, we can look for when a system is perturbed and then use the higher resolution system to kind of zoom in and provide more intensive, focused monitoring, so that you can do the higher order remapping that is the kind of work that's happening here. So the idea is, like all of the work that you've seen today about classification is based on this 50 centimeter imagery. But the lower resolution imagery, and it may be 3 meters or 2 meters, or in the future, it may even be down to a meter, that technology is going to provide the kind of passive continuous monitoring that provides the initial signal that we might want to update or focus in a particular area based on change that's detected. And that within the geospatial space is called tip and cue. That is to say, you receive a tip from the continuous monitoring system, then you queue up a higher resolution satellite to zoom in on a specific area, and then do the derivative analytics that you've heard so much about today.
Great. I think we've got a final question. We've got a few minutes before we have to wrap up, if people want to add any final questions. But this is actually a question, I mean, I think both to Caleb and others is, this is from Mathilde, who's asking, can we actually sort of go back in time? And I guess the question is, what does the imagery provide us? Andrew, you've sort of described a world where where we have more imagery, better imagery day by day, right? But the question is, how far can we go back, not just in terms of seeing what was the road network like before the disaster and inferring that, but how far can we actually go back in terms of some of the imagery? If I think back at the slide that Caleb presented in terms of some of the recent imagery that he's been looking at. So can we go back in time, and how far can we push back with, at least in this area of road detection, for some of the areas that we're looking at? And maybe Caleb, to you've seen some of the imagery. Can we go back 5 or 10 years, or is it really the future is golden, but the past is a bit murkier?
Yeah, that's a great question, and something I wish we had a lot more time to talk about. So having this land cover data and indeed other sources of data is very important at one point in time, but also getting an idea of kind of the time horizon, how things are changing, is another very important piece of data to these urban planners. And just to kind of directly address how far we can go back in time, I think 1984 is when the first Landsat reliable data came online. That's a bit low resolution compared to what we have access today. But quite far, if you want to go that far back. The high resolution imagery is to generally throw out a number around 2010.
Yeah, I mean, for sub-meter imagery, that's certainly true. We've been collecting 3-meter data for the whole planets every day or every few days since the middle of 2017 and have data going back further before that. And I'll just say in quick summary, we have not begun to extract the development insights that come from that data set. But that is to say, if you consider that we've observed the Earth at varying levels of resolution from 3 meters down to a few centimeters, going back now for at least, the last 5 to 10 years easily, there are thousands of natural experiments that occurred during that period where we put facilities in a particular place and they either were or were not accessed by remote communities that didn't otherwise have access, or where we put a road as instead of a piece of infrastructure and something happened. And we haven't reconstructed the world and extracted any of the value out of that archive, I think, as a proportion of its value. I think we might have extracted 1% of the insights that we have about the past. So there's a huge vista there, just looking over just the last 5 years, you could say, to fully understanding what we should do in the future.
Great, thanks. We've actually run out of time. I think we've got a final question from John Bevington, but maybe we'll take that one offline, or we can ping one of the users. But we'd like to thank everybody again for participating. We hope that today's presentation was of interest to you, and I think gave you a bit of a spectrum of trying to bring these types of technologies and approaches to sort of frontline use cases. You have the contacts of the presenters. Feel free to contact us if you have any particular interest. But thanks again to everybody who joined, and especially those who provided questions for discussion. Good day and a good evening to everyone.